Draft physics video. Been a while. So yeah, hopefully this week I can spend more time working on this stuff because I really, I do have it. Anyway, so this is a response to Ken Wheeler guy, the angry photographer, whatever. See if I can get him to make a video response, or to acknowledge my request to have a live conversation, and he doesn't seem to be willing to do any of this debating of his theories and the counter arguments he doesn't really want to deal with. But anyway, so I'll play some of this, I suppose, just so you get the idea of what he's talking about. But again, he's got this very, it's obviously very arrogant and yet very unwilling to have a conversation. So it's about, he uses a gyroscope made out of brass to demonstrate where you get the eddy currents and blah blah blah, and he's making some kind of claims that this demonstrates something about his theory of where the hyperboloid is hyperboloiding and all of that stuff. And I'm just saying what he's doing can be explained, and so I'll explain it the accurate way rather than his inaccurate way.
Talk about basically one
I'm based on a particle theory, of course.
of my most popular videos. I made 4 videos afterwards because I actually tilted the gyroscope along the centrifugal edge of that super powerful and gigantic monster magnet.
Yeah, so by the edge, he just means that, so say this is a magnet, the top, north, south kind of thing. So you put the gyroscope going at an angle off of this corner, and it's slowed down. So yes, everybody knows that there's paramagnetic materials like brass or copper that will become magnetic in the moment. So while they're moving, they'll acquire magnetism, and they won't retain the magnetism, they'll just have it while they're in association with a magnet. And so it's much like the fact that you can induce current in certain conductors this way by moving magnets, and it'll create magnetism in the conductor and cause electrons to flow and all of that stuff. And it doesn't slow down in the center. So when he holds it in the center of the magnet, the gyroscope spins as if it's not in a magnetic field, and when he holds it at an angle off the edge, it dampens more quickly. So that's what we're talking about here, and so that's one of his most popular videos, 74,000 views, and the videos I saw where he repeated the experiment, he just repeated it the same way. So I don't think he did anything to advance the theory, instead in the sense of eliminating the argument that I'll explain what's happening when the gyroscope is in the center, and the gyroscope will slow down anytime you put it across the field lines. So this is kind of like electricity. Like, say if I had one of those machines that creates high voltages, and so it's producing 100,000 volts, and you can put a fluorescent tube in that field. This is kind of like a boy, I haven't done this in a while, I'm forgetting everybody's name, but the guy, I don't, Tesla. But anyway, you put a fluorescent tube in the field and it'll light up. But it has to be in the field in the sense that it has to be where the polarity, the amount of the electrical potential is substantially different. So the tube not only has to be long enough, but you can't do it horizontally. So if you put it in the field horizontally, the light won't light up. It'll only light up if the two ends are further from the source of electricity, which means one of the ends is further away, which means it has a lower electrical potential. And that does relate to this in the sense that you're only going to create a dampening field in something rotating in a magnetic field if it's rotating against the magnetic field, in the sense that it has to feel both the north and the south part of the magnet in some sort of proportions. The more equal those proportions, the more it'll be dampened. The less equal, the less dampening.
I hate to use the words human stupidity, but I can't use any other words other than human stupidity. I've had thousands of comments about that video where I take this gyroscope, I spin it up, I place it at the dead center, the point of centripetal convergence over that gigantic monster magnet.
Right, so he says that's the centripetal convergence. Now what it really is a monopole. So see, he has a magnet so large. See, I could take a regular magnet, and if I take a normal sized gyroscope, I'm not going to be able to set it on here without the field lines starting to bend, which means that all the electrons and all the stuff in this atmosphere will become magnetized and lining up on the atmosphere is essentially lining up on that thing, and it's creating magnetic field that this one's initiating. So this magnet is creating essentially a magnetic field around it made of the atomic structure of the atmosphere around this magnet, and that field ends up creating what is necessary, which is a mixture or exposure to both the polarities. You have to have the polar you have to have exposure to both poles for there to be any eddy currents created. So when he takes a gyroscope, when he has a huge magnet, it means he can set a gyroscope inside the a surface that's entirely a monopole, essentially. So this magnet is only a magnet, okay, from a distance. From inside a certain distance, it's a monopole, and that's why you can essentially, well, you can actually make magnets stick. If you force a south pole into a north pole on a magnet, you can actually make the two stick, like as if they were, like the same pole will end up sticking as if they're the same pole. See, now this magnet had two different poles. I turned it around. It's sticking just as if the magnets were the same pole, because I'm essentially sticking it to a, essentially the monopole is allowing the magnet to switch its polarity, and because all it's getting is radiation of the one kind. So the point being is the radiation comes in from all directions, gravity, and in a magnet what happens is it's converted to this polarization takes place. So all the stuff that goes through this thing turns red, all the stuff going through this thing turns blue, and inside of here is basically the opposite's happening. All the red's going in here, it's coming out blue, all the blue's going in here, it's coming out red, and so it's the two are conservational. So for every bit of conversion you have coming out, you have conversions between these two poles. So I mean, you don't have any loss. It's a lossless system. But the point is that the two poles, it's essentially a monopole. So when he sets the gyroscope here, there's no exposure essentially to this south pole of the magnet. It doesn't feel it in any kind of substantial way when it's spinning this way. Now if you spun it this way, you could create the effect, because now you're weakening how much exposure there is, and they don't have the same exposure. So theoretically you could say that some of this south pole is these little, like if I put a magnet here, it will point north to south, but like I said, it gets ambiguous when you get really close to the surface of the magnet, because the influence of the south pole is so much less than the influence of the north pole. The proportions are so dramatically different in terms of how much red versus blue gets in here. So I drew this as all red, but there is a little tiny bit of blue. But the real point is on the edge of the magnet is where you start to get more and more blue mixing into the red. So when he tilts the gyroscope on this edge, what he's really doing is giving the gyroscope exposure to the south pole, and that's what's allowing the gyroscope to become polarized. Now if he tilted it this way, he's not going to get the effect. So it's only when he tilts it this way that he gets the effect, and that would be one experiment he could do to demonstrate that it's really exposure to this south pole of the magnet that's creating the eddy currents that's allowing the brass to become magnetized. It can only become magnetized when it's exposed to both poles. And that's really the secret of this thing.
Sit there and spin and spin and spin and spin. Obviously the friction of the bearings will eventually slow it down. And then I actually place it over near the edge. People actually see that I have it tilted. They're like, why don't you hold it upright? Well, I did 4 other videos months and months ago where I actually did hold it upright. And if I actually...
Well, again, I didn't see that. But even if you do hold it upright, the point is that half the gyroscope will have exposure to the south pole. So now more and more of the brass is getting polarized or magnetized. And that's creating the two forces are fighting each other. And that's why it dampens the rotation of the gyroscope, because the two magnets are now fighting each other, which is the common phenomenon in magnetic flux.
Place it along the centrifugal edge of that magnet, it will immediately start to radically slow down, and within just a couple few seconds, it's halted. That video has had countless thousands of views, and the epic stupidity, I hate to say this, you're going to think I'm so arrogant, but it's absolutely mind-blowing. I said in that video endless, numberless times.
So, again, what I'm really arguing is, I've got this written as straight lines, but you have to understand that these are the field lines, and what's really happening is if you want to create the most dampening in a gyroscope, or you want to create the most field effect in some other object, so in some paramagnetic material, if you want to make it magnetize, the best place is always where the curves are. So the more curved the lines are, the more effect you're going to have in terms of creating the polarization necessary for eddy current. So the more flat the field lines, the more likely it is the gyroscope will spin. The more curved the lines, the more likely it's going to become magnetized and be dampened.
And this is what blows my damn mind. I mean, it blows my mind to hell and back. I said countless times in that video, I said, look, centripetal magnetism is radically different than centrifugal magnetism. That is the crux and the axis mundi. It is the meat and the hamburger of that entire...
Yeah, well, whatever. The real thing is I think if you put the gyroscope right on the edge, so whatever this line is called again, but whatever, you put it on that edge here, going this way with the wheel spinning this way, you should have the maximum effect in the terms of the dampening. But that's sort of obvious. You have a lot of red here and a lot of blue here, and there's a high degree of polarization. So I don't know if we need to go through any more of this. It's just, the rest of it's just Ken blowing his own horn and such.
Our video, and yet nobody even talks about it. Nobody has a damn thing to say about it. They say, oh, that's Lenz's law, that's eddy currents. Not only is that not only a pathetic description, you don't even explain, these people don't even explain what the hell the difference is, because on a Gauss meter, I don't know if people know what a Gauss...
Okay, so again, you can't really measure magnetism without inducing magnetism. So that's the trick, right? So there's no way to measure a magnetic field without essentially creating a magnet and having it move, technically. So you essentially have to have a ferromagnetic material or a paramagnetic material, and you have to have it be affected by the magnetism. So it has to first, they have to, like gravity, it has to be induced. So the big magnet has to induce the magnetism in the other magnet. Now, if you already use something that's magnetized, you're a step ahead in the sense you don't have to induce the magnetism, and obviously then you're just going to measure the proportion of the field. So it's like the compass needle will turn. So if you take compass needles and move them around a magnet, you'll draw the field lines. You'll see exactly how much red force and blue force there is by how the magnet lines up and where it pushes to, because it has to find a balance between those two forces. So and obviously it will point straight north, and straight south here, because the amount of the repulsive force of the close thing is going to be so much stronger than the attractive force of the far away thing. So obviously, so the tail will fly out and blah blah blah. So the south will fly out, the front is heading in. They're materially connected to each other, so they can't go where they want to go. But actually, if you could cut the magnet really quick, the two ends have a momentum, so to speak, built into themselves where they would go the direction they want to go as non-magnets. So the two ends of the magnet really do want to go in different directions. They just can't because they're fixed, stuck together. So they have to have a compromise position. So that's what you're measuring there. You're not really measuring something that you're only measuring something that has to be induced. So you know, and if you're measuring with a magnet that already exists, then you're really measuring the conflict between the two magnets, in the sense that the two fields are in conflict with each other. The north side is repelling the south side of the other magnet. The south side is repelling the north side, you know, and vice versa. So you have those four interactions taking place that you're measuring with, and so it's not a perfect way to measure the actual well, it's fine. I mean, it will give you the right results in the sense that you'll know where these balances are and where, if you put a single charge somewhere, so to speak, which way it's going to go. But it's I'm just trying to point out that the measurement isn't like a pure measurement. It's a compound measurement. It requires a catalyst. Might be a better way to say that, but I'm not thinking of it at this moment.
Gauss meter is. Most people don't. It's a Gauss meter actually read the Gaussian flux. Okay, a Gauss meter will read on a huge magnet or any magnet. It is very strong in the center. It tapers off towards the intermediate zones as you reach the edge of any magnet, whether it's square or cylindrical or...
Right, but again, you're measuring the strength of the polarization, and you really can't measure the strength of a monopole. I mean, it's almost impossible to do that. So you're really just measuring the let's see how to say that right. You're really measuring the weakness of the other pole, I suppose. So I'm just trying to get to the point that it's really hard to just measure when there's such a weak influence from one side of the magnet, because the one side really doesn't have any relevance until the other side exists. It isn't until you establish the polarization in the other object, until the other object becomes magnetic. Magnets really only work on magnets. So when a piece of steel sticks to a magnet, it's not because the steel was just steel. It's because the magnet, as the steel got closer, magnetized the steel. It turned it into a magnet. At least a temporary magnet. And if you actually have contact with the magnet, you rub the magnetism off by jiggling the steel. You know, vibrate the steel in the magnetic field and it will become magnetic. Or bang it against the magnet and that vibrates the domains and allows it to become permanently magnetic. Well, not permanently, but durably magnetic. But it isn't. There's no effect until there's another magnet. Magnets only affect magnets. Magnets only affect things that have electrons and protons in imbalanced positions. Well, that's what you really have to understand, that it's really just affecting the electrons and the protons. And it depends on the positions of the electrons and protons whether or not there is a way to affect them in an imbalanced way, because there's more of them in one end or more of them in another end, and that's what you have to be able to create an effect for magnetism. It's as if the material is chaos, the magnet can't affect it because it can't reveal an imbalance in it. The imbalance you throw at it will just get absorbed by the chaos, so to speak. It's still not a perfect way to say it, but it might be close enough.
Or circular, then it increases again. Basically, it's as strong in the center as it is on the edge. The entire crux of that GD video, that damn video, is the point that with the same Gaussian flux at the center as it is at the edge, it will sit there and spin in the presence of high centripetal magnetism, but it will break very, very quickly along centrifugal.
Yeah, so again, the real real point has nothing to do with that centripetal and centripetal bullshit. It just has to do that when it's in the center, it's more of a monopole, and when it's on the edge, it's more of a dipole, and more of the brass is now becoming magnetized. None of the brass gets magnetized here. Some of the brass gets magnetized here, and that's the real difference. The magnet can only affect magnets, and until the brass is magnetized, or some of the elements inside of the brass are magnetized, it can't possibly dampen due to the magnetic force. I think that's good enough. I think I'll just end there, but yes, that's all it is. And it's just bullshit. So here's a guy who's got a video, and we'll see what his explanation is, and maybe I'll make an update. But he's mentioning this video and doing the experiment, but he might just be repeating the same bullshit experiment, so that won't be of much help. But we'll see. I'll see what he's up to and such. Anyway, so back in business here for a while, I think. Till next time.